Well, hello, AP students. So in this video, we're going to either review or learn, depending on where you are, how to interpret position time graphs, and specifically how to find average velocity and average speed from position time graphs. So let's start off simple. We have the simple position time graph here. Is this object going in the positive or negative direction? You're right. It is going in the positive direction. It's sloping up. Is it speeding up, slowing down, or going at a constant speed? I hope you said constant speed, and you could tell that because it's a straight line. Okay, so now, if we want to find the average velocity between points A and B, this is pretty easy for this example because it's a straight line. So we find our change in x, which is our change in position. Another term for that is our displacement. Over change in time. So average velocity right here is equal to our displacement over change in time. In fact, velocity is always equal to change in x over change in time. If change in time becomes very, very small, this average turns into an instantaneous velocity. And if time is big, then it's an average velocity. More on that later on. Okay, so now let's look at this. This object is no longer going at a constant speed because there isn't a straight line, it's a curvy line. And for over here, we could tell negative acceleration and this part right here because it looks like a frowny face. The curvature is negative, the curvature is down, so it looks like a frowny face. And over here, the acceleration's positive. So negative acceleration over here, it's positive acceleration because it looks like a happy face. It's curved up, so it's positive acceleration. Now, negative acceleration doesn't necessarily mean slowing down. It just means that it's negative, and we'll discuss that at a later time. Okay, so let's look at this. We are getting slower here, and then we're getting faster and slower and then faster. You look at the slopes of your tangent lines here. But to find the average velocity on a position time graph, the easy thing and the only thing you have to do is draw a line connecting the 2 points of interest and find the slope of that line. And the slope of that line is going to give us our average velocity. So average velocity is change in x over change in time. Doesn't matter what the graph is doing between A and B. It just matters the slope of the line that's connecting points A and B. Right. So let's assume that A and B are almost exactly at the same spot. They're really, really close together. So that the instant in time change in t is almost 0. So we're going to take the limit as t approaches 0. So this will create, the line between A and B will create what we call a tangent line. And the slope of this tangent line gives us our instantaneous velocity of the object at that point. So let's work out an example. From the graph, determine the instantaneous speed and velocity for a particle moving at point B. Okay, so for our instantaneous speed and velocity, well, if we want instantaneous, we're going to draw a tangent line as easy as we could. And I wish I can do this easier than, let's try this one more time. All right, that will have to do. Okay, so then we're going to look at our, let's say, That's our delta x and delta t. So this is our delta t, this is our delta x. All right, so the slope of this line goes down 1, 2, 3, 4, -4. Delta t goes over 0.1, 0.2. So the instantaneous velocity is displacement over change in time, and this is equal to -4 over 0.2, which is 1/5, so this is equal to -20 meters per second. Now speed, when you're talking instantaneous, speed can't be negative. So speed is just the absolute value of the velocity for instantaneous. So that'd just be positive 20 meters per second. Now if we're talking more average, it becomes different. Let me show you that. So if we're talking the average, if we want to find the average velocity, average speed between A and B. So here's A and here's B. So the average velocity, just like what we talked about, we connect A to B. So velocity is displacement over change in time. So from A to B, we went down. Okay, so change in x for this line, change in x is -1, and our change in time is 0.1, 0.2, 0.3, 0.4, 0.5. Yeah, we're missing a 0.4 in here, aren't we? Okay. Oops, okay, so 0.5. 1/2, so this is -2 meters per second. Okay, but now for instantaneous speed, speed is equal to distance divided by change in time. So this is very different. So over here, displacement, just for displacement, we only care about where we start and where we end. But for distance, we don't. So we go forward almost 2. Let's just say 2 to make our math easier. So we go forward 2, so it's 2, and then we're going to go backwards 2 here. Actually, I'm going to go backwards 3 all the way down here. So we're going to go forwards 2 meters, plus we're going to go backwards 3 meters, and since it's just distance, it's not negative, it's just how far we go, over our total time, which is still 0.5. So this is 5 divided by 0.5, so that's 10 meters per second. So this is a case that speed is not the absolute value of velocity. So for average, I would always go back, no matter what, go to distance divided by change in time. Velocity is displacement divided by change in time. These are our equations that will never, there's no hiccups, there's no exceptions to them, they're always true, no matter what. When we're talking instantaneous and we had to draw our tangent line here, since A and B were so close, you could pretend it was just a straight line between them. So speed ended up being the absolute value of velocity for the instantaneous. But for average, since there was a wide range in between A and B, we were able to go forward and backwards. And so we had to account for all that distance that the object traveled in this time interval. So I hope that helps, and we will see you next video. Take care.